Okay, unlike this morning, everything seems to be working. Let's see, did Dylan? Yeah, Dylan's here. Okay, so last lecture of the year, we'll just review on Friday. We hopefully will at least get to the start of galaxies. Yeah.
Sorry, I just have a quick question on the homework.
What is your quick question?
The last one, I just am not sure how the units are supposed to cancel out. Like, I got the formula.
Which one is the last one?
The find your Schwarzschild limit or radius.
Mm-hmm.
I don't know. I kept trying to figure it out, and what I was getting was not matching.
Well, for the calculation, the radius Schwarzschild is equal to what is it? G M 2G is it?
2G.
Yeah. Over C squared, right?
Yep.
Yeah.
And so that's 2 times 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared times your mass, and I said to use 100 kilograms.
Yeah.
And then the speed of light is 3 times 10 to the 8th meters per second, quantity squared. So if you look at this, now the Newton is a much shorter way of writing the units. The textbook, I think, gives you the long way of writing the units.
Yeah.
A Newton, well, first let's work with the units without simplifying the Newton. So this kilogram will cancel with one of those, and this meter will cancel with both of those because of the square. And so I'm left with units of, and I'll change colors for the next line here, maybe. I'm left with units of newtons per kilogram, and then this is per second squared on the bottom, so times second squared on top. Well, then a newton is a kilogram meter per second squared. And so now the kilograms from the newton will cancel with the remaining kilogram. These second squareds cancel with those second squareds. That leaves you meters. If you use the appropriate units, yes. Yes.
G is what?
G is 6.
No. What is that?
Gravitational.
That's gravitational constant, yeah. Not the acceleration of gravity, gravitational constant.
Oh, okay. That's why. And it should be a very small number, right?
It should be a very, very small number. Labor. It's due Wednesday. Today's Wednesday.
Yeah. You give it less.
So, yeah, it's due tonight. But if you have it turned in, you're good. Okay. Talk about Jocelyn Bell. Jocelyn Bell, after I was born, was doing her graduate research, and she noticed this signal where she had all these pulses. And so the whole scientific method, which once again on the final exam, the scientific method is something you're going to have. Same questions you had in the first exam, except for a different scenario. Scientific method, you notice something interesting, and what's the next step? Okay, we have something a little more
If hypothesis, and you test your
Yeah.
hypothesis, then if it's correct, you create another experiment to test your hypothesis. If it's not if it's incorrect, then you create a hypothesis to explain your observation.
Okay, so that's the whole process. The second step there was you create a hypothesis that has to do 3 things. Number 1 is it has to explain why your observation occurs. Number 2, it needs to be based on scientific ideas. And number 3, it needs to make predictions that can be tested. Now, Jocelyn Bell jokingly called this signal her LGM signal for little green men. The hypothesis being these are signals produced by little green men, aliens. Does that hypothesis explain where these come from? If it was correct, it would. If there were aliens out there that were, sending out a radio signal, it could explain it. And then the next question is it testable?
Really until we figure out space travel.
Yeah, it'd be pretty hard for me to figure out how to test if this was aliens or not.
We
Then
could send them signals in Morse code.
Send them signals in Morse code and hope that despite them being millions of light years away, they'll detect them soon. Okay, step 3, is this based on scientific ideas?
Not necessarily.
Okay, not necessarily, but maybe it is. Right? We know that if there are aliens out there, those aliens would be capable, potentially, of sending out radio signals just like we do. And so it could be that these are aliens. So I would not put something like this in your test because I could see people arguing both ways, and I wouldn't want to try to grade one way wrong if there's legitimate arguments both ways. But that wasn't, well, it was said in jest, but it was held as an option that it could be a contact with aliens. In fact, you might have heard of things like SETI. SETI is the search for extraterrestrial intelligence. And what SETI does is it collects signals, radio signals from all parts of the sky, and then it analyzes it looking for patterns that don't appear to be natural. And the hope is to find a pattern that must have been produced by an intelligent agency, not by some natural phenomenon. And if they detect such a pattern, then they believe they will have detected other intelligent life in the universe. Well, as she studied this, there are things to note. The period here, the number of the time between each pulse is incredibly short. This has somewhere in the ballpark of 10 pulses in a single second. 10 pulses in a single second, that's really, really quick. And so astronomers started trying to figure out what could be causing this. So starting with hypotheses, what could cause a very quick pulse of light? What could you do, Dylan, that would cause a quick pulse of light?
I have no idea, honestly. I have an idea.
Okay, what's your idea?
My idea, if I wanted to make something that blinks really fast, I could make a little directional light or like a laser and attach it to something and then spin it.
Okay, spin it. So that was one of the things astronomers looked at. They said, okay, could be something spinning. And so if it was spinning, if it's spinning this fast and putting out this much energy, it'd have to be something like a star or something. But a star would fall apart if it was spinning that fast. Because, you think about the size of a star, you get out there, things are moving super fast, it takes an incredible force to hold them in, and they would go flying off.
Because they would be moving faster than the escape velocity.
Well,
If they were seeing...
They would be, but since gravity is trying to hold them in, but yeah, I was thinking of planets, but yeah, if you're talking about a star, that's all you have to think about. They'd be moving faster than the escape velocity. So a star spinning doesn't cover it. What about a white dwarf? We studied a white dwarf. Even white dwarfs with their size, the outer portions would be spinning so fast that gravity wouldn't be able to hold it together and it would fall apart. And so the only spinning object that remained that potentially was possible was a neutron star. Now, unfortunately, Eliezer took us directly to the correct answer.
Sorry, what a coincidence.
Other things that scientists looked at were maybe it is a star that has something else passing in front of it. Well, if something else was passing in front of it, orbiting around it, you would have exactly the same problem. That thing orbiting around it would fly away. So it couldn't be something orbiting around it. What about a star that's getting brighter and dimmer?
Okay.
Right, like a flashlight. That was my thing, was I could have a flashlight go, beep, 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 beep. I can make really quick pulses. Well, if it's a star making these pulses, a basic rule of thumb is the period is going to have to be longer than the time it takes for light to go from one side of the star to the other side of the star. Simply because you have light from the equator or the edge and light from the center, and the time it takes light to travel that distance needs to be less than half of the period of your oscillation. And it turned out stars are too big for light to travel across the star during this period. And so that left them with neutron stars as the only option. So the conclusion is it must be a neutron star that is spinning. Now these things were named pulsars because they were pulsating stars. Now, scientists are really not tricky sometimes. They think they're funny sometimes, but generally they try to be obvious. And so here's an example of a pulsar. I actually saw a YouTube video of an astronomer with his demonstration of a pulsar. And he takes an electric drill and he puts a flashlight in a bunch of tinfoil and puts the electric drill on that, turns it on so the tinfoil is spinning around, the flashlight's going. That's basically the idea. The idea is it's like having a lighthouse that's going around. And of course, the lighthouse only points in certain directions. But as it comes around, if it points at you, you see the pulses. So a pulsar must be something like that, we believe. It is a neutron star that's rotating around, and if its light beam passes over the Earth, we see it pulsing. Instead of saying it's a neutron star, we say it's a pulsar. So pulsars are just neutron stars that we're observing in the right way. Now, how in the world does it make its light?
That's the thing I always wondered about this section.
Until the section when I read it? Is that what you're saying?
Well, I always wondered because I'm like, well, stars don't just like give off light in general.
Well, now remember, a pulsar isn't a star. A neutron star is not a star. I know it says star, but it's not. It's neutrons held up by neutron degeneracy in what used to be the core of a star.
So the main thing is it's no longer burning anything.
Right, it's no longer fusing anything. Here is a picture where you can see the neutron star, and you see the lower of the two objects inside of that. Okay, that color didn't work out. Magenta always stands out. The lower of the two objects inside that circle, you don't see it all there. So it's getting brighter and dimmer so that you don't see it in some of the frames and you see it in others. That's the pulsing. And you'll notice that this pulse is not the same at all as that pulse. So this only shows one cycle. If we saw two cycles, we'd see that this repeats over and over again. So it only has two shapes that alternate back and forth. What does that suggest to you if you have two different profiles that alternate back and forth?
You've got two different sides you're looking at.
Yeah, two different sides you're looking at, and they're not exactly the same. Okay, so how does it make that light? I think this is where we have it. Nope. We have instead our first clicker question. You cannot answer yet. You can answer now. This was, I believe, a homework question. Uh-oh. Not everyone got the homework right, it appears. Okay, we had 1, 2, 8, 0. I'm positive. It says that it just disconnected. Again. I tell you, I had so many problems this morning. My cable didn't work this morning. Let me go back to... I brought in a different cable So if it was a bad cable, this one here will still work. Please show up. Already doing better than this morning. I ended up not using my tablet because everything failed this morning. Okay, so the majority answer here was it slows as energy is lost. Now, that's the correct answer. What's going on? You have, and we haven't gotten to the slide on how it's made. I'm worried I might have taken it out. So I'm going to go over this, and then when I come to the slide, I'll say I just went over it. You have a star with a strong magnetic field. As it dies, all of this material that's swirling around making magnetic field starts collapsing to the center, and the object starts rotating faster. And what happens is that magnetic field gets multiplied. It gets really, really large. So you have a star that had a really strong magnetic field, and when it goes through its type 2 supernova and ends up with a neutron star, that neutron star has an extremely strong magnetic field. And it's rotating really quickly because it went from being mini solar radii down to being the size of the city of Lincoln. So it really got smaller. To conserve angular momentum, it has to be rotating extremely quickly, doing, as much as hundreds of rotations per second, which is really scary when you think about something rotating that fast, being that big. It is then, because it has such a strong magnetic field, that magnetic field, as it rotates, is going through space like this. The magnetic field, it turns out, doesn't have to be along the axis of rotation. If the magnetic field is like this, the magnetic field is flashing through different parts of space. And as that magnetic field comes around, particles that hit that magnetic field have to change their motion in response to the magnetic field if they have a charge. And those particles, their motion is actually what is producing what we call synchrotron radiation. And so that's how the radiation is produced. It's the magnetic fields interacting with particles and then creating radiation. But of course, that's energy leaving. So if energy leaves, it's just like my bank account. If money leaves, what's left for the money in my bank account? There's less. Energy leaves the pulsar, its energy drops. And how do we see that energy? We see it in its rotation rate. It slows down as it loses energy. Yeah.
Would B not be right then? Like, would it be considered wrong?
You are correct that B is incorrect.
Okay.
B is not right. It's not losing mass.
But isn't it a reason that could attribute to a pulsar's period decreasing over time? Because I thought the reason that it spun so fast was that it wasn't losing mass, but it was shrinking in depth.
Well, it spins so fast because the mass comes to a closer diameter. If the mass was not part of a solid object, it really wouldn't matter. If mass leaves and it's not a solid object, it's not going to affect what's left. If it's a solid object, then it would.
Okay.
But it speeds up because of the mass falling in.
Right.
But then the mass can't leave. It's stuck.
Oh, okay.
Right. It's not like a dying star that's blowing mass off.
Oh, okay.
There's no outward. Now it's spinning really fast, but anything that
not an option that you can consider.
yeah, anything that can't hang will be lost when it spins down to become the pulsar to begin with.
So,
Go ahead.
as it loses energy, the star slows down, the neutron star slows down?
Yes. The same would be true when you're running. As you lose energy, you slow down, right?
Yeah.
It's Seth goes flying when he gets tired.
Wings of eagles. Well, just because, from what I understood, none of the energy that it's actually projecting is actually doesn't actually belong to the neutron star.
Well,
From what I thought I was reading.
it's starting with rotational energy of the neutron star.
Okay, so
Rotational.
when it says energy, it's talking about the rotational energy.
the rotational energy of the neutron star is what's making it come around, which is making the magnetic field interact with the particles around it to create the synchrotron radiation. But that interaction puts a torque that slows down the rotation.
That makes sense.
Okay, glitches. If you observe a neutron star's rotation speed, you find that it generally slows over time because it's losing energy. But then there are these little glitches where suddenly it speeds up. Now, based on the answer to the last clicker question, if you reverse that and it speeds up, what would that say to you? Getting energy from somewhere. But how would it do that? And how would it do it in pretty much an instant? Right? I mean, it is possible to have something like a white dwarf with a companion or a neutron star with a companion and have material fall in that speeds it up. In fact, we're going to talk about that. It's observed with neutron stars. But that's a process over time. This is instant. So scientists following the scientific method have explored one method after another and finally came to the conclusion that what must be happening is the neutron star must be collapsing a little bit. When it collapses a little bit, just like when Seth was on the stool up here, you bring the mass a little bit closer to the center, and what happened to Seth's rotation rate? He sped up. So the conclusion is that these glitches where the spin rate increases are because it's shrinking a little bit. What's a neutron star like? First, the size. 10 kilometers or about 6 miles in radius. That is reasonably similar to the size of Lincoln City. Right? About 12 miles from one side to the other. So a neutron star would just about fit within the city limits of Lincoln, more or less. But how big is the mass of a neutron star?
Like about the entire solar system.
More than the entire solar system.
Well, including the sun?
Yeah.
Whoa. That's really cool.
And so that's really, really dense. The density of the neutron star is the same as the density of the nucleus of an atom. And so if you had a teaspoon of neutron star material here, it would weigh tons. Right? It's extremely dense. And the inside here is, it says, a neutron superfluid. Let's not worry about what that means. What it means is you have these neutrons packed really tight. The exterior is supposed to possibly be iron. Why iron? Well, it was the endpoint of fusion that was giving off energy, so it seems like there should be some there according to calculations. So here is the actual description of how they create the radiation. Yeah, let me skip past this. I don't want to talk about magnetars right now. And instead, ask you 3 questions in quick succession. What size of star becomes a planetary nebula as it dies?
There's only one answer.
There is only one correct answer. Okay, we did not have very good congruence here. 4, 1, 2, 2, 1, 2. The Flip Friday apparently wasn't fully successful.
It's just a lot to remember.
Well,
Was it A or
but
B?
it was neither A nor B. Okay, so let's talk about these real quickly. What is A? What falls within the range of A?
Nothing that is a star.
Nothing that is a star, but also nothing that is a planet. That's the brown dwarf region that's neither star nor planet. So these are brown dwarfs. .08 to 1 solar mass. Those are small-sized stars.
Small lower end main sequence.
One to
Below
what was that?
star is?
I didn't
Aren't
understand.
those below what really a star is? Like, in between a planet and a star.
The brown dwarfs, yes. Right. Brown dwarfs are not stars. They're in between planet and star. And that's where the LT comes in. The LTs are for brown dwarfs, not for actual stars. Okay, then 0.08 to 1 solar mass. Well, the sun is at the top end there. Those are going to be stars. The upper ones will actually fuse hydrogen into helium and then helium into carbon. Right? If it's above half the solar mass, they'll fuse helium into carbon. But calculations suggest that 1 solar mass is just about the minimum for planetary nebulae. So 1 to 8 solar masses has to be the one that has planetary nebulae, since 1 solar mass is kind of the limit. Some astronomers believe the sun will become a planetary nebula. Others believe it will not. It's, that close. Why is 8 the upper limit for planetary nebula?
Because I'm sure that will collapse back into itself.
What happens if you have more than 8 solar masses during the living period?
It'll become a red giant. Crap, I was wrong.
It won't become a white dwarf. It will undergo instead a supernova. And if it undergoes a supernova, it can't have a planetary nebula. Because the planetary nebula is the gas that was ejected during the giant stage then being lit up by the radiation from the final death without having a supernova. So 8 to 20 was supernova. What about 20 to 150?
Isn't that like the hypernova?
Yeah. Hypernova, those have enough mass that when they die, they'll have a supernova type explosion but become a black hole instead of a neutron star as the core. And then what about greater than 150 solar masses?
Not a star.
Well,
You haven't been able to find
yeah, what did it say? I don't remember exactly what it said, but
What it said is it had so much mass that it wasn't stable
yeah,
ever.
it would get hot and keep material from falling into it or something like that. So what would end up happening there, I assume, is you would end up blowing material away and then you have less and you become a large star if you start with more than that. So those are the pieces we had there. Now, remember I said there are 3 in quick succession. So here's another one. Hopefully we learned something from that one.
How long does the black hole last?
A black hole lasts, if it's isolation, a very, very long time. If it's not in isolation, forever.
Wait, how is this different from the last one?
Because this is what size of star becomes a neutron star when it dies. The last one said has a planetary nebula.
Oh.
Do we have to enter it? Oh, no.
I mean, we don't get graded off if we get it wrong, do we?
No, you just break my heart, that's all.
Okay.
That's worse.
Yeah, I don't like grading here. He probably can't, but I can.
I could regret. They turn that home.
One more, Seth. Okay, good choice. 0, 3, 3, 6, 0, 0. Now, on the last slide, I wrote here supernova type 2. But what does the supernova type 2 leave as its remnant? A neutron star. So the correct answer there was 8 to 20 solar masses because they're going to create a type 2 supernova and a neutron star. Okay, the last of these three quick ones. What is the minimum mass for a black hole? I know a student came to me a little bit perplexed asking about this, so it's, I think, a good question. No, there's only one correct answer. Oh, I don't know what you answered.
Oh, I know you watched it on there. I think in my head was maybe not. Well,
Well, the clear consensus here is that it's not 0.016 solar masses. Sarah, what's the correct answer? It's what? What do you think the correct answer is? Oh, not 8, no.
I put the theory
Zero.
in.
It's what? Not 0.08.
20.
One.
Not 20.
1.
150.
There is no.
There is no minimum mass. Now,
Oh,
But
man.
0.016 is so small that it's like having no minimum.
It's
No.
not actually that so.
that's a lot bigger than the mass of Earth. Okay, there is no minimum for a black hole. However, there is a minimum for a black hole to form naturally. Right? If it's going to form naturally, you have to have enough mass to crush through everything, and that's somewhere around 3 to 4 solar masses to crush everything. So for a star to die and become a black hole at death, it has to be 3 to 4 solar masses. But God could turn you into a black hole, which is why we did that homework problem. God's not going to do that.
Wow.
Just, I have that kind of confidence in him. Or her.
We went into it, right?
Hey, what?
We would become a very, very, very small amount.
We become very, very tiny. Now, let's just take as an example, let us suppose that Cody, my student TA last night, he really did something wrong. Instead of being struck by lightning, by the way, and crushed him into a black hole. Approximately how big would Cody be when he got crushed into a black hole?
He would be like dust particle size.
Way smaller.
He would be like electron sized.
Are we talking like quantum? Quantum particles?
Let me ask Labor, because I know he has the
He would
answer.
be too upside down.
How big would Cody be if he was crushed down to be a black hole?
Dark matter. Dark matter.
Remember? Okay. He would be smaller than anything known in the universe.
Smaller than an atom?
Way smaller than an atom, yes. So, if Cody was crushed down to become a black hole, what would happen to Satish?
Oh God! So these would be
Nothing.
identified.
Nothing.
I'm with Seth. What's happening to Seth right now? How much is Cody attracted him?
Nothing.
It's immeasurably small. If Cody was crushed to be small to be a black hole, his mass doesn't change. So he would still attract Satish with the same force.
Yes, but wouldn't he fall to the ground?
Well, Cody would be much smaller than the atoms in the space between them. So Cody
So he would just fall through it.
would fall straight through the floor. He'd be smaller than a neutrino. He would just fall through the floor toward the center of the Earth.
You all thought that was
And anything that got inside of his Schwarzschild radius, he would assimilate. So random collisions, he would probably build up a little more mass as he got towards the center of the Earth. don't in the center of the earth. There's a lot of liquid in there, so it's more likely to pick up mass. And I imagine eventually we would have the center of the earth would be a black hole. That's the remnants of Cody.
How's it going?
Meanwhile, on the surface of the earth, the only thing that we would really notice would be magnetic field would disappear if we lost all that liquid material that's swirling around making our magnetic field.
My question is, okay, so black holes, like you said, only affect their like source radius. But does that radius grow as they simulate more mass?
Okay, one thing is incorrect, one thing that is. The thing is incorrect. They still affect things outside of the Schwarzschild radius. A black hole is, the Schwarzschild radius is defined as the radius where light cannot escape. Right. It has a very strong gravitational pull for things that are close. As you go farther away, it falls off as 1 over r squared. And so, with Cody's mass, you know, from you to him is way too far for it to be a measurable force. So that's why you wouldn't have a problem. But if instead of Cody's mass, we had the mass of the Earth, like if the Earth was crushed into a black hole, well, we feel that force. That pulse is pretty strong, right? And so if the Earth was suddenly crushed in a black hole, we'd be up here without anything holding us up. We'd fall down on it, right?
But, okay, so I guess then, like, what I'm asking is, if Cody were to turn into a black hole.
Yeah, the second half.
Yeah, oh yeah.
The second half was the correct part. The Schwarzschild radius depends on the mass, as we saw with that problem. So, as a black hole pulls more material in, its mass increases and its Schwarzschild radius increases. So, a black hole that has material around that it can assimilate, that it can pull in, will grow. And when they grow, you have fun things happening. You have, like, in the center of the Milky Way galaxy, I know I'm not going to get there, so I'll just talk about it here. Center of the Milky Way galaxy, there is a black hole that's, what is it, 3 million solar masses or so? It's a lot of mass, right? The mass of 3 million stars. Clearly that was not a star that died. That's something that formed when the Milky Way galaxy formed, probably. And so there are stars swirling around, and of course if you get close to that, the tidal force is very, very strong. That is the difference in force from something close to something farther. Like, you know, your head and your feet. If you're jumping in feet first, your feet are going to be pulled more than your head, and you're going to get stretched like spaghetti. And you'll be millions of kelvins in temperature because of that stretching. Translation, you can't survive going into a black hole. And keep in mind, a wormhole is 2 black holes linked. So you also can't survive going into a wormhole.
You didn't tell me that Interstellar was not completely scientifically accurate.
And they had Kip Thorne, who is one of the world's experts on black holes, as an advisor, but I guess they probably didn't take his advice that, well, your movie's so stupid.
Well, I don't think the purpose of the movie was to present
Reality. It was to present a curved reality where you have somebody sends a coded message to tell him, oh, you should go here. So he goes there and everything is first, so he's sending himself that
Keep in mind that he wasn't in charge of the storyline.
What was your question?
It was bad. Oh, so my question then is, would your, like, theoretically speaking, if you could somehow survive the whole blah blah blah, would the gravitational pull on your feet versus your head, wouldn't that just like tear you apart, or would your body be able to, because of time and space?
Your atoms would be pulled into a very long, thin string. I mean, when we say spaghettified, it's not like you're a rigid piece of spaghetti. You'd be like a whole bunch of atoms that are pulled out.
So, well, I guess what I'm asking then is, in theory or whatever, you wouldn't just like rip into a
I don't know what would kill you first.
Right, but what I'm saying, like, if you could, if all that you had to worry about, if you could isolate all of the factors and just focus on this stretching aspect, would your, like, is the stretching within physical limits? So, like, once you stretch to a certain point, your body would just, like, or would your body, like, actually extend because of some weird other phenomenon?
I'm pretty sure you would be disarticulated first and then go from there. I haven't thought of this as a means of torture, but
The CIA has been sending people into black holes for information. We want information on you.
All right. So,
I feel like this, whenever this is a book, I was kind of let down. I was expecting something a little bit better.
okay, how does a black hole work? The original formulation of the idea of the black hole simply came from, Thomas More, theorizing, hey, if you get more and more mass in a smaller and smaller region, then the escape velocity gets bigger and bigger. You've already learned about escape velocity. And so he said, well, if you get enough mass packed in a small enough region, the escape velocity can reach or exceed the speed of light, which means that light can't even escape. So he said, I'm going to call that a dark star. A dark star because light can't escape from it, so you see the star, but you can't see any light from it, hence you don't really see it. But you can detect it. Then we have a lot of variations and people learning more, and we get to Albert Einstein. And Albert Einstein comes up with this theory that we really live in a four-dimensional space-time continuum. We tend to think that we live in three dimensions. I have that direction, and that direction. Three mutually perpendicular directions. We call that three dimensions. But Einstein said time is just the same as those three. So we live in four dimensions instead of three. Three of them are spatial dimensions that we can easily manipulate. I can walk this direction all I want, or I can walk this direction, or whatever, right? Jump up and down. But I can't manipulate time. But according to Einstein, they're all intertwined. Now, quick time out. Theological note.
So God is extra dimensional?
I believe that these four dimensions of space-time that we live in were created by God when He created our universe. And so time is not a dimension for God. And if you think about that, it makes a whole lot of sense. To God, our entire universe is kind of like a cube where time is on one dimension and x is on one, y is on one, and z is on one. It's just a four-dimensional cube to Him. And so He can obviously see the beginning from the end because it's just all this one cube. Likewise, He could be anywhere at any time. He could be everywhere at any time because He can easily just manipulate through those dimensions that are not of His realm. So to me, the concepts of omniscience and omnipresence, they don't bother me at all because they make perfect sense. If God is outside of our universe, He can interact with us.
It would be the only logical thing. If He's outside of the universe.
Yeah, if He's outside the universe, it's the only logical thing that He would have those. So anyway, coming back to the physics now, just wanted to interject that because to me that helps me to understand how I interpret the Bible better. Einstein's saying that we have this space-time continuum and that we could give up a little space for time or give up a little time for space allows you to do things like warping the space-time continuum. How many people have ever heard some sci-fi say, warping the space-time continuum? Okay, that is a real physics term. To take this four-dimensional space-time and put it into an easy-to-understand analogy, we say, okay, consider a sheet of paper. If this two-dimensional sheet of paper represents the four-dimensional space-time, then I can take this paper and I can bend it, and that's warping that space-time continuum. And in fact, I can warp it around and make two pieces of paper touch, and then if I can somehow move from one side to the other side of the paper, what would I have just done? I would have just had warp travel. Warp travel, the idea is to bend the space-time continuum, so you have two very far separated locations that because of the warping are right next to each other and then somehow punch through from one space-time to the other space-time. That's the whole idea of warp travel. There is real serious research done to try to do that. Okay, so this warping the space-time continuum idea is illustrated up there with the idea of a bowling ball on your bed. You have the bed, it's flat, a two-dimensional analogy for the four-dimensional space-time. You put the bowling ball on there, the bed warps. And that's the idea of mass, according to Einstein, warps that space-time continuum. It bends it. And if you put enough mass, you can actually make that space-time continuum warp all the way around it. So that according to Einstein, the Einstein black hole is not just a region where the escape velocity is greater than the speed of light, but it's a region where space has actually bent around on itself. So you could think like if you're inside that black hole, you can run all day long in a straight line. You'll never get out because it's like being on the inside of a basketball. You can run all day long on the inside of the basketball and go all kinds of distances, but you never get outside because it's folded over itself. And so that's the Einstein view of a black hole. What's going on inside a black hole? Yeah, we have no idea. Well, you would be torn, all your molecules would be torn apart before you fell in. But once you fall in, who knows what's inside? So here's my grand theory. I've actually seen other people propose this, but I proposed it before I saw anyone else do it. In geometry, astronomy,
Wow.
we see a lot of things occurring over and over in different scales. We see things like a solar system. Well, let's start with, we have the Earth with the moon orbiting around it. Then we have the sun with the planets orbiting around it. And then we have, well, we're not part of one, but we have clusters of stars where they're all orbiting around each other. Globular clusters have black holes in the center, they're all orbiting around a black hole. We have galaxies that are just bigger but like clusters. You have a black hole in the center, everything's orbiting around that. Why not go the other direction? Why not make black hole, actually it's not going the other direction, let's keep it on. A black hole, we're inside maybe a black hole. So that our universe constantly has energy coming in. There is one of the things we're not going to get to, this thing called dark energy. It turns out that by the best measurements, the universe is expanding and accelerating expansion, which means energy is coming into the universe, which physicists can't really explain. But if we were inside a black hole, then material falling into the black hole would perfectly explain the increase in energy for us. Really no good way to disprove my wacky theory. And like I said, other people have posited.
It's a hypothesis.
Okay, hypothesis.
But it's a good hypothesis. I like it.
Yeah, I love it. It gives me joy.
So what if we're just a bubble like what Einstein proposed that happens in space-time that warps in on itself? I think I've seen that before. It's just kind of like a bubble that hangs out of space-time.
I don't know.
That's how I've seen it represented before.
Oh, goodness. I'm on slide 12 of 46. Well, got to 13.
My final paper, don't I?
Yeah.
Okay.
Oh, my word.
How do we view a black hole? By definition, you can't see a black hole, right? Go back to the dark star idea. You can't see it because light cannot come out. Yeah.
I just have a quick question about your theory. Now that I'm thinking about it, how would we presume that energy is entering the universe through the black hole, though all we can see is that it is going towards it?
Well, we can see, this plays into this. We can see a black hole if it has material nearby. If it has material nearby, that material nearby orbits around it, and as you have collisions and whatnot, it loses energy and falls in. And so eventually, and now once again we get to Einstein, Einstein's theory says that material falls in just regularly. But for those of us far away, time runs at a different rate, and we see it slow, slow, slow as it gets closer and closer. So that if you were to fall into a black hole, and you had a wristwatch that was perfect and worked in all conditions, I would see your wristwatch slow, slow, slow. And I would see you never enter the black hole. Your wristwatch would just slow until it seems like it's not moving at all. And you never get in. But for you, your wristwatch would just keep running normal. When you get to the time that I see it frozen on, that's when you passed on in.
That's when you pass the horizon. Now, universe of that looking out away from the black hole until the point where
We couldn't see outside the black hole. If we're inside the black hole, we can't
no,
see
no,
outside.
not inside it yet. Before you reach the event horizon, does the universe look then like it's moving faster?
To you, actually, I'm not ready to talk about that simply because I haven't thought about it, and we got 1 minute. It takes long to get my thoughts straight. We can see a black hole because we can see stuff going around and falling in. And when it falls in, you have stuff that gets ejected along the rotational axis of the black hole, so you have big bursts. So the black holes at centers of galaxies will light up, giving off like thousands of times more light than the entire galaxy when something big falls in. Okay, we're out of time.
Next Flip Friday.
There will not be a Flip Friday.
Just one present.